Everything looked fine until memory ran out in our Node.js app. It's an article written by Osman on his Medium page. And I'm interested in this because I have an app that I'm building with Node.js as the backend. When memory errors suddenly started crashing our Node.js BFF service, we knew something unusual was going on. This post shares how we tracked down the leak, what helped us solve it, from heap snapshots to a surprising permission issue. The memory leak incident. During our code freeze period, we encountered a memory leak incident. Our service started throwing errors due to memory exhaustion. As a quick fix, we restarted the pods, which temporarily resolved the issue. When we examined the memory graph of the publication on Grafana, we noticed a pattern that looked straight out of a textbook. Grafana is an open source analytics and monitoring platform. Memory leak analysis. First, we asked ourselves, why didn't we catch this earlier? The answer was tied to our deployment frequency. In staging, deployments happen often and pods get recreated frequently, essentially hiding the leak until now. We checked our other applications and didn't observe the same issue there. Even in our pre-production environments, we couldn't replicate the behavior. While reviewing the packages we use in the affected services, one stood out: IO Redis. Digging into its GitHub issues, we found a discussion that suggested a possible memory leak in its caching logic. At this point, we had a strong suspicion, but we didn't want to drop a long-used package without evidence, so we moved on to profiling, one of the most effective ways to confirm a memory leak. Memory leak profiling, do it yourself. While researching profiling methods, we came across several tools and approaches. We decided to take heap dumps ourselves and analyze them. We used a heap dump package and created the service to trigger dumps whenever needed. Here's the code. So you import heap dump, and there's a memory dump service that you can use. With this service, we were able to capture the application's memory state as a heap snapshot file on demand. Note: heap dump write snapshot may block the main thread for a while, especially in large memory apps. Consider offloading this to a work thread using Node.js's worker threads module. Dump analysis. Let's take a peek inside. We triggered the service at different times and analyzed the resulting dumps using Chrome's DevTools memory panel. Chrome DevTools memory panel helps track memory usage, capture heap snapshots, and detect memory leaks. You can observe memory allocation over time and monitor garbage collection behavior, critical for performance tuning. For a detailed guide on using it, check out Record Heap Snapshots. Okay, a lot of this I've never used before, but it's really interesting seeing how the process they went through to resolve this issue, identify and resolve this issue. We compared snapshots using the comparison tab in the memory heap snapshot section on Chrome DevTools. This made it easier to spot retained memory and class level differences. Here's a look. Okay. I don't really know what I'm looking at. Snapshot list. This section shows all the... Okay, number 1, snapshot list. This snapshot shows all the heap snapshots you've captured or uploaded. Each snapshot includes a timestamp and file size. It's useful for tracking how memory usage changes over time and for selecting snapshots to analyze or compare. Chrome DevTools supports uploading only one head snapshot file at a time. 2. Constructor comparison mode. This area displays objects grouped by their constructor. It's most useful in comparison mode, where you can compare two snapshots to detect growth in object instances or memory usage. Constructor indicates the class of the object. Repeated names can hint at leaks. Delta shows how many instances were added between two snapshots. A growing number suggests a potential leak. Allocated size, total memory allocated to objects of that class. 3. Retainers. This section shows the reference chain keeping each other alive. It's extremely helpful when trying to understand why something isn't being garbage collected. Retained size, memory that won't be released until the object is garbage collected. This is the most important metric for detecting leaks. Distance to the garbage collector route. Lower distance means the object is more likely to stay alive. In our case, we saw repeated chains like first in, second in, third in. These string objects were retained as part of a long reference chain, preventing the garbage collector from cleaning them up. What did we discover? While investigating the heap snapshots in detail, we discovered a large number of string objects that resembled serialized JSON logs. Most of them contained payloads typically sent to New Relic, including structured data like timestamps, request metadata, and status codes. Here's a simplified example of one such log object. These strings weren't being actively used by ongoing process, but they were still being referenced somewhere in memory, forming long reference chains that kept them alive. Their retained size grew to several megabytes, far beyond what we would expect in normal operation. So what did we discover while investigating the heap snapshot? We discovered a large number of strings objects that resembled serialized JSON logs. Okay. Their retained size grew to several megabytes, far beyond what would expect them in normal operation. The actual New Relic log file existed on disk, but logs were being written to it. That led us to suspect a file system level issue. Eventually, we found that the application didn't have write permission for that file, so logs were being buffered in memory indefinitely. This explained both the memory growth and the GC retention. The logs were stuck in a queue waiting to be flushed, but the flush never succeeded. How do we fix it? As part of our security policies, some file operations had restricted permissions. We updated the file write permissions, and the application returned to stable memory behavior. Due to high memory usage, containers were frequently hitting their memory limits, causing pod restarts. Once the root cause was fixed, the memory usage dropped significantly and stabilized. After deploying the fix, we observed a clear, consistent drop in memory usage across all 6 pods in our 6 data centers. Before, memory usage under load peaked at around 530 megabytes. After, memory usage stabilized at 140 megabytes. That's a big drop down, with occasional spike up to 250 megabytes. Improvement. Overall memory usage dropped by approximately 73%. This significant drop not only confirmed the fix, but also improved system stability and resource efficiency across environments. Container memory. Can we compare this to what we had earlier? Yeah. It was peaking up to 512 and averaging around 300, and now it's only peaking up to below 300. That's amazing. Conclusion. Memory leaks are hard to detect in frequently deployed environments where pods restart often. In our case, the leak was silent and only revealed itself during a rare code freeze. This experience reinforced how essential it is to have good observability. Take memory snapshots when things look off and go beyond assumptions when debugging. Profiling tools like Chrome DevTools and well-timed heap dumps turned out to be critical in understanding the issue. If you're running a long-lived Node.js service in production, proactive monitoring and periodic heap analysis might save you before your memory runs out. And there are some references. And this is such a cool article to read. I love seeing small contained problems like this. What issue that caused, how it was identified, and how the cause was identified, the investigation into that, and what the solution was. So I loved reading this.